Okay, section 3.4. We're going to talk about the z-scores. A z-score is a standardized score, standardized value. We will always, regardless of how many digits you start with, we will always, always, always round to 2 places. Okay, so what a z-score does for you. Probably some of you probably in here took what was called, I think, the DSP, is that right? The Delaware State Testing thing. And you got a score of like 1 to 4. Remember that? A score of 1 to 4? The DSTP, okay. I don't think they're giving that anymore. So a score of 1 to 4, well then how do I compare your score on that test to your SAT scores, which range from, what, 200 to 1600? Completely different scales, right? Totally different scales. Or how would I compare that score on that test, which goes from 1 to 4, to your IQ score, which we know ranges probably somewhere from 55 to 145, right? Different scales. So how can we compare them? Well, that's what we do with z-scores, because z-scores are going to normalize those scores. Regardless of the scale that they began in, they're going to normalize them so that we can compare any sets of data. So for our sample, obviously it's going to be the value of the data minus the mean, x bar divided by S, which of course is the sample standard deviation. For population, the only thing we change again is it's x minus mu divided by theta. When I move my screen, only part of it moves. That is the strangest thing ever. It separates my, nope, that it didn't, okay. Weird. So interpreting z-scores, guess what? It's the exact thing we just learned. It's the exact same thing we just learned. Because a z-score is really a standard deviation. They're one and the same. If I'm 1 standard deviation away, I'm 1 z-score away. If I'm 2 standard deviations away, I'm 2 z-scores away. They are the same. They are the same. And last section, we learned that ordinary, our usual values, lie between 2 standard deviations from the mean. Those are usual. We also learned that unusual ones were above +2 and below -2. So it really says the same thing, just in different vocabulary. Ordinary values are between -2 and +2, and unordinary or unusual values are greater than +2 or less than -2. So here's our normal curve. These are the same as z-scores. They are z-scores. But mu, whoops, or x bar, depending upon whether it is a sample or if it is a population, when we normalize them, our mean is in the exact same middle, isn't it? It's going to be 0 for a z-score. Okay? My mean will be equated to 0 for a z-score. Okay? To make it work out with the formula, we just said the z-score would be equal to the value minus the mean divided by the standard deviation, didn't we? So if my mean of some, okay, take the IQ scores. Say that particular person's IQ is 100, and I'm going to subtract the mean. What's the mean of IQ scores? And this is equal to 0 divided by the standard deviation. It doesn't even matter what the standard deviation is, because 0 divided by any number is 0. So that's how my mean, whether it's a population or sample, becomes 0. Okay, one standard deviation away again is a z-score. One z-score away. Okay. By the way, I have these blank curves on your Blackboard site, so if you want to print them off so they're already drawn and you can add things to them, you certainly can do that if you don't want to have to draw that curve every time. It's just there for your convenience. And again, the exact same thing we just learned. But they're saying they're z-scores, and they put them in decimals. We're going to round it to 68%, 98%, and 99.7%. Exact same thing we just learned. We use the word standard deviation. Standard deviation equates to our z-scores. Okay? There you go. There's one for you to try. Marty measured his pulse rate to be 48 beats per minute. Is that pulse rate unusual if an adult male pulse rate is mean of 67.3 and the standard deviation is 10.3? Guys, go ahead and try to answer that question. We'll come back and look at it together. Okay, well, I'd like to get you into the habit of drawing these out, because a drawing is worth 1,000 words. And the better you do it and the more you do it now, the easier it is going to be to translate it to when we have to find areas under the curve. And those really need to be drawn, okay? So if I'm going to draw this, I'm going to put my normal curve. And this is going to be my center, correct? And I know that the mean is 67.3, and that's the population, so 67.3. But my z-score there is 0, correct? Okay, one standard deviation away. I need to add, what am I adding? The standard deviation is 10.3, so I'm going to get 77.6. Everybody good? One more standard deviation away. By the way, my z-score is 1 there, yes? And I'm going to add standard deviation of 10.3 again, and I'm going to get 87.9. And that is a z-score of 2. So then I have to build the other side of my curve. I'm going to take 67.3 and I'm going to subtract 10.3 and I'm going to get 57.0. Okay? And I'm going to go one more. This is my -1, correct? Then I'm going to subtract, that looks like that number all ran together there. Sorry about that. 57.0, and I'm going to subtract 10.3, so I'm going to get 46.7. That is when my z is -2. Okay? His rate that he found was 48 beats per minute. Where would he fall there? He's usual, isn't he? Because 48 is what? Between 46 and 57, so we'll put him right here, right? So he would be usual. Anything out here in this tail, anything out here in this tail would be considered unusual. So percentiles. How many of you in here are trying to get in the nursing program? Anybody? Got one? Okay. When you take, now it's called the T's instead of the NLN. We used to use the NLNs. We will give you points on your ranking based upon percentiles. So percentiles is not the number you got correct out of the total number. That's a percentage, right? It's not a percentile. A percentile puts you on the normal curve where you are compared to everybody else. That's what a percentile is. So if you got in the 90th percentile, that means you scored better than 90% of the other people taking this test. It didn't mean you got 90% right. Okay, difference between your score on your test and a percentile. Okay, to find a percentile, we're going to take the number of values. We're literally going to count how many data points there are less than the one we want and divide that by the total number. And of course, we're going to multiply by 100 to make it a percent. Okay? So here we go. Back to our good old Chips Ahoy cookies. I should like bring in Chips Ahoy cookie. We talk about them so much, right? Geez. So we need to find the percentile for a cookie with 23 chips. So I'm going to look through my data. And here's the first one with 23 chips, correct? So I need to count how many, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 pieces of data that are less than 23. I'm going to divide by the total number of pieces of data, and there's 10 and there's 4 lines, so obviously there is 40. So I'm going to divide by that, and of course you already know if I take 10 and divide by 40, I'm really going to get 0.25, correct? If I times it by 100, which means really I'm taking from a decimal to a percent, so 23 is the 25th percentile, and that's how I'll write that. No, it's the one less than. Okay. See a couple of you still writing. Absolutely. Okay, because first I did, everything's in order. Then I located, I want the percentile for 23 chips. So I located this one, number 23. Okay, and I want the percentile. I want to find the order in which it's in. Now that makes more sense, the word order. Okay, so that made more sense. So I counted how many there were that were less than 23, and there were 10. How many total? 40. Okay, good. Sometimes if I change vocabulary, it helps, right? Good, good. Questions are great because it's going to help the people at home too, because they can't ask questions, right? Okay, because if you score in the 90th percentile, that means you scored better than 90% of the other people. So it's that the dividing line is between the one just lower than you and the one that's above you. So you have to go with those that are less. Those that are, remember, always compared to those that are less. Because if not, look how many 23s I have. Which one do I pick? Ah, see? Yeah. What's less? If we said 25, we would do right here and then count. Okay, so the question was, what if you were trying to find it if there were 20, this percentile of one with 25 chips? So we'll put that in red. And just like I did before, I'm going to look through my data and I'm going to determine that this is where the first 25 chip cookie starts. So now I'm going to count my number of pieces of data. So do we agree this first whole row is 10? Second whole row is 20, 21, 22. So my percentile would be 22 divided by 40. So I times that by 100 because that's my decimal, right? So I would write that is it's at the 55th percentile. Is the location of the number in order. Just like when you score on a test, if I look at an entire population, the test scores are going to be normally distributed. Okay? And if I scored in the 90th percentile, that means that I scored better than everyone else that scored something below me. That test score could be 198. But this would represent everybody that got 197 or less. Does that help? Okay. So you can always put it on a normal curve. It really, truly. Good. Okay, and then sometimes we have to convert from the percentile to and find the location. So to do that, it's really what I'm doing is I'm finding a locator. And I'm going to take the percent or the k, divide by 100 because that gives me back to a decimal. Then I'm going to multiply by the number of pieces of data. So let's do that. We're going to have to go back to the previous data. Let's say that from this Chips Ahoy, whoops, I can't move it. If I do, I lose it. Okay. Let's say that I want to locate the percentile for 26 chips in a cookie. This time I'm not telling you the percentile. You have to find the percentile. Okay? It's giving you backwards. So I want to know the percentile. Well, no, I said that backwards. I apologize. So let's give me the percentile. I want to find the percentile of how many chips are in the percentile of 80%. What is the 80th percentile? How many chips would that cookie have? How many chips would the cookie have that were at the percentile of 80? Okay, so I have to figure it out. First, I'm going to take what? I keep doing that, and I can't do that. Really, he's being quite finicky. Now I can. So P of 80. Your formula says I'm going to find my locator. The position is really my locator. Is equal to 80 over 100 because I'm really just putting that percent back to a decimal. That's all that's doing, right? And I'm multiplying it by the number of total values. How many total pieces of data do I have? 40. When you do that, you get This is equal to my locator. It is not equal to the number of chips. It is equal to my locator. So now I need to go back to my data and find 32 in. So let's count. Row 1 is 10, 20, 30, and here we go. 31, 32. Well, 32 would be 26, wouldn't it? But the problem is I have 26 that comes right next to that. So really I would have to say it's 25 because it was that many less because they are duplicated. If this were 26 and this were 25, I definitely would say that. But because they're the same, I have to go back to the one less of 25. So it would be that it would be the 26 chips, but because it falls here, I just have to know that it would still be, the one below it would be 25. That would be the percentile, the 80th percentile. Okay? Yes. Correct, because it was duplicated. The 26 was duplicated many times. Yeah. So that's not the best data set to give you an example, but because we had a lot of repeats. It would be the 20. It would be 25. Mm-hmm.
So if the locator would have came up as 30.
Right. Correct. If it was 30.
The 30th position is 26, so it would be the one right next to it, which is 25.
Okay. Okay. All right. All right, so this was just a real quick chart of showing you how to do that. I just showed you how. Okay. All that leads us, though, to quartiles, and the quartiles is going to lead it to some formulas, but more importantly, the quartiles are going to lead us to be able to build what's called a box plot. Sometimes it's referred to as a box and whisker plot. Okay? So the first quartile, second quartile, and third quartile. Well, the first quartile is what? The 25th percentile. The second quartile, well, guess what? Because it's exactly midway, it's 50%. The whole, it's really the median, or it's the 50th percentile. And the third quartile would be the 75th percentile. So really, I'm taking all my data and dividing it into fourths. All the pieces of data and dividing it into fourths. That's what my quartile says, like a quarter is to $1. Okay? All right, so we've got our minimum value. We have our quartile 1, our quartile 2, which is our median, our quartile 3, and our maximum value. Here's some other statistics that you can calculate given those quartiles. One is called the interquartile range. We're going to use that interquartile range a lot because that's how we're going to find out if something's considered to be an outlier, similar to when we were considering if something was unusual or usual. Okay? So we're going to be using that to determine whether something is an outlier. The semi-quartile range is just that divided by 2. Midway is I'm going to add them two together and divide by 2. And if I wanted to say something like that, I can always use percentiles to state it. Okay? Here's what we need to build our box plots. It is called the 5-number summary. You need your minimum value, your quartile 1, your median, your quartile 2, and your quartile 3, and your maximum value. Box and whisker. So the way we build our box and whisker is we're literally going to have a box. This is going to be our median, which is again the same as quartile 2. This is going to be quartile 1. This is going to be quartile 3. You'll have a minimum value here. You'll have a maximum value here. And you literally draw a line. A box and whisker plot. Five-number summary, the minimum, quartile 1, quartile 2, quartile 3, and maximum. That's why we need our 5-number summary to build that box plot. Okay. That's an oops with the thing. I've already really told you there how to construct it. Here's the same picture again. We know if we're looking at this data, we're looking from this box plot, we can read this from the data that's given. I have data that has a median of 68. Its lowest value is 4.5 with its maximum value being 225. And I have my quartile 2 and my quartile 3. Also, what we can tell from a box plot is whether something is normally distributed. What's your gut say about that one? It's not. What way is it skewed? Where's my long tail going to be? To the right. So it's going to be skewed to the right. Why? Because my long tail is here to the right. I've got a data point pulling me way out to the right, to the high end. So I can actually look at a box plot and determine if something is normally distributed. They should be mirror images if they're normally distributed. For instance, you know my drawing is bad, so I keep preferencing that, right? That would be something that's normally distributed. The median is in the middle. Quartile 1 and quartile 3 are equal distance from the median. The minimum values aren't way stretched out. Okay? That would be something that would be more normally distributed. There's one much better than mine. This was a random sample of the heights of women. There's a skewed distribution. This one happens to be thousands of dollars in salary of NCAA football coaches. I wonder who this is way out here at the end, right? So here we have to determine if something is an outlier. An outlier is an unusual value. We've talked about usual and unusual. An outlier is an unusual value. It's something way out to either side. Could be way low, could be way high. It can have a very dramatic effect, as we've seen in the past, on the mean and the standard deviation. Okay? With that, with a box plot, if we determine something has an outlier in it, we're going to reconstruct the box plot and call it a modified box plot. We're going to plot them, but they're not going to have a line connected. So we'll do that. Now, way we're going to find out if something is an outlier, we have to do the calculation. We have to do the test. We can't just say, well, it looks like it to me. Okay? 1.5 times the interquartile range. So this, I'm going to take the Q, the third quartile, and I'm going to add 1.5 times the interquartile range. And here I'm going to take quartile 1 and I'm going to subtract 1.5 times the interquartile range. So anything above this or below this would then be considered an outlier. Above or below would be considered an outlier. So as I said, we would sketch them a little bit differently. A modified box plot. I think I have one on the next. Yep, here we go. Modified box plot. You can see where these two particular data points were determined using our 1.5 times the interquartile range were outliers. So I can still plot them, but then I'm going to use my next value lower, that's within my interquartile range, to be my whiskers of my box plot. And I'll just show those other 2 points do exist. But I'm not going to draw my whisker out to the outliers. Okay? So we covered a whole lot about data. Just for a summary slide here, because, you know, at the end of this is our ending point. That will be our tests, chapters 1, 2, and 3. We've talked about the context of data. In other words, where do we come from? Is it that important? The source. Is it coming from the M&M's company selling their M&M's and saying there's more reds than browns? Which there are. What kind of sampling method was used? What are some of our sampling methods? Somebody tell me one. Cluster. Stratified. Systematic. Random. Convenience. Convenience sample is not one I want, right? That's not a good sampling method. We've talked about measures of center. Somebody tell me measures of center. Mean, median, mode. How about variation? What did we talk about for variation? What are some of the measures? Standard deviation. And what about the range? The range is another measure. The unusual values, that's going to be my outliers, the distribution, and the outliers. What about distributions? Can they have a normal distribution? What other kind of distribution? Skewed. I can have skewed left, skewed right. Is there any other? Uniform. Uniform distribution, meaning, hey, the temperatures of Hawaii every month of the year, right? Between 80 and 85. That would be a uniform distribution. Changing patterns over time. Do those change? Yeah. Can we illustrate them? That's a time series graph, isn't it? And conclusions and practical implications. You know what? We may know something, but does it really matter? Is it a practical thing? Okay? Okay. Good. We'll do a sample of a box